Hello from my side. A warm welcome to my webinar on securing modern vehicles with AUTOSAR. I'm Michael. I'm working as a senior security consultant and lead technical officer for AUTOSAR security at Scrypt. I'm working for Scrypt since 2016, working mostly for customers from the automotive world, helping them secure their products. My special interests are naturally AUTOSAR security, but I'm also interested in general security concepts and key management. And I'm also a member of the AUTOSAR Consortium, where I'm a member of the working group security since 2018, and where I was also recently appointed the speaker of working group security. Let's start with a talk. And I would like to start with these two colleagues, Charlie Miller and Chris Walasek. I think most of you are familiar with their work on the GPAC, and I don't want to go into detail on what they did. I think that's pretty well known, but I would like to point out two consequences that their work had. The first consequence is that security is now pretty much in the focus of the automotive industry, and security gets the attention that it deserves. Every OEM and Tier 1 is trying to make their products as secure as possible. The second consequence is that more and more researchers started looking into automotive security, and we can see that by the number of publications that have been published since then. This is just these are just some examples and all of the papers that are shown here, they are focusing on different vehicles from different manufacturers, but in the end, they have all more or less the same attack going on, and I would like to show you what kind of attack all these researchers are carrying out. So for this, let's start with some generic vehicle that has an ECU with external interfaces, for instance, an infotainment ECU with Wi-Fi or Bluetooth or the like. We also have a gateway or switch that that connects the ECUs within the in-vehicle network, and we have an ECU that we would like to attack, the powertrain ECU. So what does the attacker do in order to attack this ECU? Well, first, the attacker starts to attack the external interface, and he tries to exploit a vulnerability such that he can gain access of the application that implements this external interface. Once the attacker has control of this application, he tries to extend its rights to have privilege escalation by exploiting a vulnerability in the operating system's kernel to gain access of the complete ECU. Once the attacker has reached this goal, he can start infiltrating the in-vehicle network, cross domains to reach the critical ECU, arrive at the powertrain ECU, and in the end, attack the ECU. Now, what can we do in order to protect against such an attack? Well, first of all, we can harden the ECU. This is especially true for the ECU that implements the external interface, so the infotainment ECU in this example. Second, we should secure the in-vehicle communication to make it for the attacker as hard as possible to cross the domains and to reach the critical ECUs. And finally, we should also think about the complete life cycle of a vehicle and also try to keep the vehicle secure when it's on the road. Now, these three items are for sure not the complete truth. I think in order to holistically secure your vehicle, you need more items, but these three items are important items, and more importantly, these three items are items that I can cover within one webinar. So let's focus on these. And let's try to focus on how can we secure the vehicles within these measures with the tools that AUTOSAR gives us. And with that, let's have a look at AUTOSAR. Let's start with a brief introduction into AUTOSAR. First of all, what is AUTOSAR? AUTOSAR is a standardized middleware for automotive ECUs, and it comes in two variants, classic and adaptive AUTOSAR. Classic AUTOSAR focuses on safety use cases and on real-time requirements. So classic AUTOSAR is focusing on typical microcontroller use cases. Adaptive AUTOSAR, on the other hand, is focusing on providing more performance while still providing safety to a certain extent. So within this regards, Adaptive AUTOSAR was more designed to deploy it on microprocessors. I would also like to point out here that adaptive is not meant to replace classic, but both are meant to coexist next to each other. And in fact, both can even coexist next to each other within one ECU, as we can see here on the right-hand side. We can see here an example architecture of a vehicle computer that features a microcontroller that runs an instance of classic AUTOSAR, which in turn hosts applications with high safety requirements. And next to it, we have a microprocessor, which runs a hypervisor, which then in turn runs several instances of different OSs. So we can again see one instance of classic AUTOSAR for safety use cases, two instances of adaptive AUTOSAR. One could be for automated driving, the other one for vehicle to X communication, for instance. And we could even have a non-AUTOSAR platform here, like a Linux platform, for instance, that could host applications from the infotainment domain, for example. So after the what, the why. Why use AUTOSAR? Well, AUTOSAR is pretty much a de facto standard in the automotive industry. It's broadly accepted and widely used throughout the whole automotive industry. Also, with regards to security, AUTOSAR provides off-the-shelf security building blocks that can be used for several use cases. We will have a look at them in a second. And thirdly, AUTOSAR is also a living standard. It's kept up to date. There are yearly releases, and with every release, so maybe not with every release, there's a new security feature, but with lots of releases, new security features are introduced. But every release also brings in some optimization of already existing security features. Let's have a look at classic and adaptive in more detail. Classic looks like this. So if you have already had experience with AUTOSAR, you might know this picture because it's very colorful. Classic AUTOSAR is based on a real-time operating system, which is called OSAC, and it follows the layered software architecture. We can also see that here on the left-hand side, where in red, we can see the microcontroller driver layer. In green, we can see the microcontroller abstraction layer, and in blue, we can see the service layer. Classic AUTOSAR was defined for microcontrollers, which means that the classic AUTOSAR code can be directly executed from Flash, and which also means that the memory layout is statically defined already at compile time. Classic AUTOSAR, once compiled, is also monolithic. So everything is run within the same context, which means that you cannot isolate individual applications within classic AUTOSAR. Everything is just run within the same context. Next, adaptive AUTOSAR. Adaptive AUTOSAR looks like this. It's less colorful, but at least we have still these nice boxes. Adaptive AUTOSAR is based on a POSIX-compatible operating system. So this could be Linux, QNX, Android, and the like. And already here you can see that there's quite a difference between classic and adaptive AUTOSAR, because these operating systems we know from desktop computers, from smartphones, and so on. So we can already see here that these operating systems offer much more performance than typical real-time operating systems focusing on microcontrollers. Adaptive AUTOSAR also does not follow the layered software architecture, but does provide functional clusters. So the functional clusters are these boxes here. And these functional clusters are designed towards the application. So the functional cluster possesses application-exposed interfaces. And the specification also describes their behavior, but how all these interfaces are connected to the hardware, that's not specified within adaptive AUTOSAR. This is left open to the implementer to make this implementation as efficient as possible. In contrast to classic AUTOSAR, adaptive AUTOSAR cannot be executed directly from Flash, but the code has to be dynamically loaded into RAM first. And in order to do so, AUTOSAR also does the memory allocation dynamically, not statically like classic AUTOSAR. And also within adaptive AUTOSAR, applications can be executed within processes, which allows you to isolate each and every application within a process, within the virtual memory space, which allows you to separate applications between each other and also applications from the stack. So the point that I would like to convey here is that both platforms, classic and adaptive AUTOSAR, are based on fundamentally different architectures, which means that some security controls are only needed in one of the two architectures, and even the same security control could look different in both architectures because the basis is just so different. And so I have tried to denote this within the remainder of this talk, where I've put some C or A in brackets of the security building blocks to denote if this building block is available in classic or adaptive AUTOSAR, or both. Okay, so with this in mind, let's go back to the attack and let's try to protect the vehicle, and let's try to do that using AUTOSAR. Let's start with the first part of the attack on the external interface and the attack on the whole ECU. And let's try to harden that ECU. So what can we do to harden this ECU? Well, first of all, we can make sure that only trusted code is executed. How can we do that? Usually, this is done by employing secure boot mechanisms, and AUTOSAR also supports you here. This feature is called Trusted Platform and is only available in adaptive AUTOSAR. The Trusted Platform feature is a feature that uses OS-specific tools that support you in ensuring code integrity. So one example would be dmverity that is supported in Linux, and that works directly on individual memory pages and does the code integrity check in the moment that this memory page is loaded into RAM. So this is a very efficient approach, and these approaches are available in the operating systems used by adaptive AUTOSAR. So this is a feature that's only available in adaptive AUTOSAR. Next, you also want to make sure that the application has only access to the interfaces that the application really needs. So you want to have fine-grained access control. You can again realize this by OS-specific tools like SELinux, AppArmor, and the like. But AUTOSAR also supports you here with the module Identity and Access Management, and I will tell you more about this in a second. Finally, it's also a good idea to isolate your application from other applications and from the stack. You can do this using separate user IDs, using containers, using sandboxes. This part is not standardized within AUTOSAR. AUTOSAR does provide some recommendations what should be done, but how this is done, this is a decision made by every implementer of the adaptive AUTOSAR stack. So there's no building block available for this. That's just how you implement this. And if you want to use adaptive AUTOSAR, I think it's a good idea to check on how this is realized and if this is compliant with your requirements. Okay, let's now have a deeper look at identity and access management. And I would like to start here with an example. Let's assume that we have an ECU where the COM stack provides a door control service, and this service is consumed by the door control application. So that's fine, I think. Now let's assume that an application has been compromised, and this application also wants to access this door control service. So clearly this is something that you do not want to have, and this is where identity and access management comes into play. Identity and access management manages an access control list that describes which application is allowed to access which interface. So in this case, the access control list would state that the door control application is allowed to access this interface, and the compromised application is not allowed to access this interface. So in this example, then the compromised application would be forbidden to access this interface. Now, summarizing again, what does identity and access management do? Well, it enforces access rights. These access rights are deployed together with the application in the form of signed manifests. Identity and access management manages these access rights, and based on these access rights authorizes applications to access specific services. And this works with local applications and remote ECUs. Local applications can be identified based on their process IDs, so with the help of the underlying operating system. Remote ECUs can be authenticated using by establishing a secure channel, by using TLS or IPsec. You can also just trust the remote ECU based on the IP address. However, I think that's not a good idea because there's no authentication involved and IP addresses can be easily spoofed. Okay, let's now go to the next step in the attack. Let's now have a look at the secure in-vehicle communication. How can we secure our in-vehicle communication? Well, the first proposed measure here is to deploy domain separation. What does that mean? Domain separation means that you group ECUs into group ECUs with similar use cases or similar criticality onto the same physical bus or the same VLAN, and reduce the amount of cross-domain communication as much as possible. So every ECU is basically only allowed to talk with a group of ECUs with similar use cases or similar criticality. It's also a good idea to enforce this domain separation by deploying a network firewall, for instance. Now, this domain separation feature, this can be supported by AUTOSAR using gateway functionality and so on, but in the end, this is something that has to be designed by the OEM when designing the EE architecture. So there's no security building block available that can you help to really implement this domain separation, but this has to be done by the OEM at an earlier stage. The second proposed measure that I would propose here is ECU authentication. So you want to make sure that the ECU that's talking to me is really the ECU that I expect it to be. So I want to authenticate the ECU. And AUTOSAR supports you here because AUTOSAR supports a number of secure communication protocols like SecOC, TLS, and IPsec that are actually both available in classic and adaptive AUTOSAR. So let's have another look at this. As already said, AUTOSAR supports SecOC, TLS, and IPsec as secure communication protocols. TLS and IPsec are focusing on Ethernet communication and are coming from the enterprise sector. SecOC actually was designed within AUTOSAR and is focusing on typical automotive bus systems like CAN, FlexRay, and the like, but it can also be used on Ethernet. Secure communication is implemented within the AUTOSAR COM stack and also configured within the AUTOSAR COM stack. This means that secure communication is transparent for the application. The application just uses the COM stack without being aware if the communication is being secured or not. And the COM stack then takes care of securing the communication depending on its configuration. So this feature is just transparent for applications. I would also like to point out that secure communication is always relying on cryptography. You need to have cryptographic primitives to compute a MAC, to sign something, to encrypt something. And this is provided by the crypto stack. The crypto stack provides AUTOSAR standardized interfaces that abstract the underlying crypto implementation that could be done within an HSM, for instance. And the Crypto API provides interfaces to access cryptographic primitives, but also cryptographic keys. And here's also one point that I would like to make, because I've had talks with OEMs where they said, yeah, I want to have secure in-vehicle communication. I want to have a concept for SecOC. And yeah, key management, we also want to have that. And I have the feeling that key management is not always getting the attention that it should get, because key management is really a crucial aspect of secure communication. And if you don't take care, you might end up with some vulnerabilities that can lead to exposure of keys. And with that, your in-vehicle communication is immediately broken. So I'm talking about using fleet-wide keys. I'm talking about not exchanging keys when you're replacing an ECU, thus creating clones of keys. This is something that should not happen, that can easily break your secure in-vehicle communication, so please take care of that. Finally, the crypto API is not limited to secure communication, but the APIs can also be used directly by applications for their own application-specific use cases, like encrypting some data, for instance. Okay, great. So we now have an idea on how we can secure the vehicle. We have an idea of measures to deploy, and let's assume that we have protected our vehicle using these measures. But what if a vulnerability in our infotainment ECU firmware has been found that allows code execution, which means that our ECU hardening measures are not working anymore? What if, in addition, TLS is broken? So our in-vehicle communication isn't secure anymore. And what if an attacker takes these two vulnerabilities to perform an attack on our vehicle and is successful because he can just ignore our carefully crafted security controls? I think this is a scenario that we should take into account, because looking at the lifetime of a vehicle with 10, 15, 20 years, it might happen. So we need to also take measures that the vehicle is also kept secure when it's on the road. And how can we do that? Well, the first thing that we need is an intrusion detection system. So we need to be aware of what's going on the vehicle. If there's an attack going on, for this we need an IDS that detects ongoing attacks and forwards them to the VSOC, to the Vehicle Security Operations Center. So this is just a team of security experts that's monitoring the fleet and that's analyzing attacks and deciding about countermeasures. One of these countermeasures could be an IPS, so an intrusion prevention system. This allows you to manage security controls within the vehicle dynamically. So for instance, adapt firewall rules to block an attacker reaching a specific ECU. Another control could be just updating the firmware. You know, if there's a vulnerability in the software, just patch it. So update the ECU firmware, and this needs to be done over the air in order to not get all the vehicles into the garage. Software updates over the air are supported by AUTOSAR. An intrusion prevention system is not supported by AUTOSAR, but an intrusion detection system is. And I would like to go into detail more for the IDS. So how does an IDS work? Let's again have a look at some generic vehicle with a number of ECUs, and each ECU has to have IDS sensors. IDS sensors are just small pieces of code that monitor specific resources like network traffic, like CPU usage and the like. And depending on rules, the IDS sensor can then raise a security event if it thinks an attack is going on. One can also think about deploying smart sensors, so sensors that are not just monitoring one specific resource and doing simple rule-based security events, but a smart sensor can monitor multiple resources. So you can think about a firewall that monitors the complete Ethernet bus and all the messages going on there, and that does complex filtering, complex analysis, complex correlation, and based on this analysis, a smart sensor can also raise security events. Security events need to be analyzed by the VSOC, so this team of security experts that analyzes these events and decides about countermeasures. So what's missing here is the architecture, how to get the IDS sense, the security events, to the VSOC. So what's missing here is an architecture for an in-vehicle distributed IDS. And you can see here one example architecture that consists of two elements, the IDS-M and the IDS-R. The IDS-M is the IDS manager, and the IDS-M collects and aggregates and qualifies security events on every ECU. So we can see here the IDS-M is available on every ECU. The IDS-R is the IDS reporter, and it aggregates security events on vehicle level in contrast to ECU level for the IDS-M. And the IDS-R is also the module that's connected to the VSOC and forwards the security events to the VSOC. With regards to AUTOSAR standardization, the IDS-M is standardized within AUTOSAR. This also makes sense because the IDS-M is needed on every ECU, so you can really leverage the standardized nature of AUTOSAR here. The IDS-R, on the other hand, is not standardized within AUTOSAR. It's foreseen within the AUTOSAR concept, but this module is not standardized. And from my point of view, this also makes sense because you just need that once within the ECU, and yeah, you don't need to distribute it that broadly. So yeah, the AUTOSAR standardization that doesn't give you that much benefits here. Okay, let's now have a deeper look on how the IDS-M works. The IDS-M qualifies security events based on the filter chain. We can see that here on the right-hand side. We can see that there's this filter chain here on the left with different filters. Every security event has to pass the filter chain, and after the filter chain has been passed, this security event is considered qualified. So there's now a qualified security event, or QSEV. This QSEV can then be stored persistently on the ECU, or it can be forwarded to the IDS-R such that it is transmitted to the VSOC. And in order to transmit it to the IDS-R, AUTOSAR has also standardized a QSEV protocol that describes how the QSEV has to be formatted in order to be sent on the bus. Basically, this also concludes all the security building blocks that are available currently within AUTOSAR. But I've also said that AUTOSAR is taking care of trends in the automotive industry. So what is AUTOSAR currently doing, and actually what are current trends in automotive? I think there are currently many trends like electrification, automated driving, and so on. But one trend that I would like to highlight is also a trend in EE architecture. Within EE architectures, we can see that coming from modular distributed EE architectures, like here in the bottom, where every ECU implements a specific use case, we can now see a trend that these use cases are collected on vehicle computers, on high-performance vehicle computers. And we can even see that on these vehicle computers, even different domains are collected. And one example of such a future EE architecture is a zone-based EE architecture. A zone-based EE architecture is an architecture where you divide the EE network into geographic zones. So, for instance, front right, front left, rear right, rear left, and to connect these zones via high bandwidth internet. The main idea behind the zone-based EE architecture is that you don't need the wiring harness anymore. The wiring harness is an element that's quite expensive and heavy, and if you can get rid of that, you just save immediate costs. So that's the main driver behind the zone-based EE architecture. What do we need to build such a zone-based EE architecture? First of all, we need high-performance vehicle computers. We can see them here in the center that do all the computation for automated driving and the like. We also need domain controllers for every zone that do all the routing, that do already some pre-computation of sensor results and so on. So these domain computers also need to be quite performant. And we need lots of Ethernet because we have now lots of communication going on between all the different zones. And in order to realize this, we need lots of high bandwidth Ethernet. This high number of Ethernet also requires new security controls, namely MACsec for authenticated communication and a firewall to provide access control on network layer. Let's now go to through these two. Let's start with MACsec. MACsec is a secure communication protocol that operates on data link layer, so on OSI layer 2. This means that all higher level protocols like IP, TCP, UDP, SUMIP, and so on is directly protected using MACsec. We can also see that here on the left-hand side, where only the MAC addresses are outside of the secured frame. All the rest of the Ethernet packet is secured with MACsec. MACsec supports authenticated and confidential communication, but it does not provide end-to-end security. It only provides hop-to-hop security from one physical entity to the next physical entity. And one key point of MACsec is that it supports high bandwidth. This is due to the fact that MACsec can also be supported on hardware level. So there is MACsec-aware hardware available that provides hardware acceleration for MACsec, and only with this it is possible to provide this high bandwidth that's needed for zone-based architectures and to secure all of this communication. Next, firewall. Here I would like to spend some more words on, because this is an activity that's actually put forward by us. So maybe first of all, some words on motivation. Why did we start a firewall standardization activity? First of all, we think that this is needed. Looking at zone-based EE architectures, and we think a firewall is definitely needed in order to secure this, and this firewall needs to be distributed in the vehicle, so AUTOSAR standardization makes sense. Second, we have also the feeling that we need a common understanding on how to describe a firewall and how to configure a firewall, because we always see that when talking to customers and discuss with them what they expect from a firewall. Everybody has a different understanding and has a different formulation, and this creates a lot of pain on synchronizing the requirements. And we think that this can be resolved by agreeing on a common language, on a common understanding on how to configure a firewall. And that's also one of the main drivers why we drive the firewall standardization in AUTOSAR. Okay, getting back to the firewall. What does a firewall do? The firewall serves as an additional security layer to isolate and separate in-vehicle traffic, for instance, by enforcing VLANs. A firewall can block illegitimate communication to individual ECUs or the entire network. A firewall can also be used to control access to the in-vehicle network by external entities, for instance, by diagnostics or charging stations or the like. The firewall can also help you keep your network alive by protecting against denial of service attacks, and a firewall supports you in detecting intruders, so it can raise security events and support your intrusion detection system. Within the scope of the firewall standardization, so there are different deployment scenarios possible, right? A firewall can be deployed on individual ECUs as a host-based firewall, but it can also be deployed on a switch as a network firewall. Our standardization activity focuses on the host-based firewall. So why is that? The main reason is that we can write a functional specification. We can deploy AUTOSAR on the host-based firewall, and we can write a specification for that can be implemented within AUTOSAR. For the switch, we cannot do that because switches don't usually run AUTOSAR. You can imagine doing that, but that's not the main use case of AUTOSAR. So we don't want to write functional firewall specification for a switch. However, talking again about this common language that we would like to establish, this language shall also be applicable to switches. So the idea basically is that in the end, we have a common understanding of how to describe firewall rules. And using your AUTOSAR tooling, you can also just create an Ethernet switch, assign this switch a set of firewall rules, generate an RxML for that, and hand that over to your switch vendor. And the switch vendor can then take this RxML and can transform it into a format that is readable by its own implementation. And bam, there it is, your switch is configured. So basically, that's the idea of how we can also include firewalls on switches using our AUTOSAR standardization activity. Let's now have a closer look on what functionality we would like to standardize. We would like to standardize filters within 3 categories. First, stateless filters. So the firewall inspects network packets and compares header fields against statically defined allowed values. Second, stateful filters. So this means to take into account the stateful nature of some protocols, for instance, TCP, and filter on attacks against the state machine in order to protect against a SYN-ACK flood, for instance. And third category, we would also like to standardize filters on the application level. So to provide the packet inspection. And you can also see that on the right-hand side, we have listed all the protocols where we would like to provide filters together with the category. In addition to that, I've also listed the planned features for the firewall. I think I've already talked a lot about the standardized format for firewall filter rules. Another feature that we would like to add is context-based filtering. So what does that mean? Basically, the in-vehicle traffic of a vehicle is strongly dependent on its current state. So this means depending if the vehicle is currently parked, if it's currently driving, if it's currently in a diagnostic session, the in-vehicle traffic is expected to be quite different. And the firewall should be aware of this and activate or deactivate filter rules based on the current vehicle state, such that diagnostic messages are only allowed when the vehicle is in a diagnostic state. Furthermore, we also want to standardize rate limiting in order to protect against denial of service attacks. And we would like to standardize security events to support the intrusion detection system. For the firewall, we have planned the first release for this year that's only focusing on adaptive AUTOSAR. And for next year, we have then planned to also add the release for classic AUTOSAR. Finally, on this slide, you can see one example of how we imagine that these firewall filter rules could look like, where basically for one firewall filter rule consists of a pattern, where for every protocol you define the expected value. So for Ethernet, you can define an expected source MAC, expected destination MAC, expected ether type, and so on. From this, you just generate a complete pattern, match all the network packets against a list of patterns. And once you have a pattern match, the firewall performs an action. So this could be that the packet is passed or dropped, that a security event is raised, and so on. So that's more or less about it. That's what's in AUTOSAR. So let's summarize. I've started with this attack on vehicles, and we have discussed on how we can protect the vehicle against such an attack. And we have said that on the one hand, ECUs shall be hardened, where AUTOSAR supports you with the trusted platform and the identity and access management modules. We've also said that the in-vehicle communication should be secured, where AUTOSAR supports you again with secure communication protocols like SecOC, TLS, IPsec, and soon MACsec, which is supported by the crypto stack, and we will also have the firewall soon that supports us here. And finally, we've also said that the vehicle shall also be kept secure when it's on the road. And for this, we have also two modules that AUTOSAR supports us with. That's the IDSM and the SOTA, so the software update over the air. At this point, I would like to take one step to the side and talk again about the UNECE. I think we are all aware of the UN regulations 155 and 156 that require OEMs to implement a cybersecurity management system. But in addition, it also requires OEMs to provide proof of adequate security in order to gain vehicle type approval. And actually, the deadlines for this are quite soon. So the deadline for new vehicle types is basically now, and the deadline for all vehicle registrations is already in 2 years. Now, within this talk, I think I've shown you that AUTOSAR provides quite a number of security building blocks that can be used to provide adequate security. And we thought that, well, to which extent can AUTOSAR actually fulfill the UNECE requirements? And we have made an analysis, and basically that's the result. Here on the left-hand side, you can see a list of all the mitigations that are listed in the Annex 5 of the UN R155. And on the right-hand side, you can see all the security building blocks that are offered by AUTOSAR, and we have rated them basically to which extent does this security building block implement the mitigation proposed by the UN R155. And again, we have rated them into categories. 1 point means that this building block supports you in fulfilling this mitigation. And 2 points means that this building block really does a good job at implementing this mitigation. So I don't want to go into detail here because we have written a white paper on this. If you're interested in that, you can read the white paper. The link is on the next slide. The point that I would like to convey here is that there are a lot of points on the right-hand side, right? So AUTOSAR really provides you support in implementing the mitigations required by the UN R155, which means that AUTOSAR really supports you in providing the adequate proof, the proof of adequate security that is needed for vehicle type approval. So if you're interested here, again, have a closer look at the white paper or just approach us if you want to talk more about that. So finally, that's the last slide. Within this talk, I think I've made my point clear that I'm convinced that a layered security approach is needed for holistic security of modern vehicles. And I'm also convinced that the AUTOSAR security building blocks can be used to implement such a layered security approach. However, it's not always that easy. The security building blocks have to be used in a right way. You cannot just take SecOC, throw it on your vehicle and say, look, the vehicle is secure. The building blocks have to be used within a security concept. So for SecOC, you need to know which messages to secure, how do you want to manage the freshness values, how do you want to manage your keys. Also with regards to IDS, you need to have an idea of what resources do you want to monitor, what security events do you need in order to have a good idea of what's going on within your vehicle. And if you're working on this and if you need support here, I think we can help you here because we do know the AUTOSAR security building blocks. We are a member of the AUTOSAR Working Group Security since 2018. We have done multiple projects with several OEMs and tier ones on SecOC, on key management, on IDS. We also provide AUTOSAR security trainings if you want to know more about the AUTOSAR security building blocks. And we also have products that are AUTOSAR compliant. We have an IDS system with an AUTOSAR compliant IDSM. We have an HSM with AUTOSAR compliant crypto driver. And within the company Ethos, we are also offering complete classic and adaptive AUTOSAR stacks. So if you're interested in that, on the right-hand side, you can see again the code that leads you to our site. We can find the white paper, where you can find our service offering again, and we can also find contacts that you can approach if you need support. And with this, I would like to thank you for your attention. Goodbye.